Hello, welcome to this video about heterocyclic chemistry. This is the first of 3 videos in which we're going to look at the reactivity of some 6-membered heterocycles. To start off with, we're going to remember how in a pyridine system the aromatic ring is constructed. So for an aromatic system we need 4n plus 2, or 6 electrons in this case. Those 6 electrons come from the double bonds in the pyridine ring. That means that the lone pair is not involved in the aromatic system and instead is in an sp2 hybridized orbital. This means that it is the HOMO of the nucleophile, which means it is nucleophilic and basic. This is one of the most important reactivities of pyridine. That means it will react with all kinds of electrophiles and acids to form the corresponding pyridinium salts. For example, if we start off with a pyridine, we have those 3 bonds for the aromatic ring, giving us our 6 electrons. That means the nitrogen lone pair is not involved in the aromatic system. So if we introduce a good electrophile, something like HCl, so an acid, then the lone pair will react with our H plus in our acid. That will give us the pyridinium salt, where we have NH plus in our 6-membered aromatic heterocycle with a Cl minus counterion. Alternatively, if we add in electrophile such as methyl iodide, now our high energy lone pair, the HOMO, will break that carbon iodine bond to make a new nitrogen carbon bond, which gives us the methyl pyridinium salt with an iodide counterion. We can do the same kind of reactivity with an acid chloride. Again, our aromatic system does not include that lone pair, so the lone pair is nucleophilic, and it will attack the electrophilic acid chloride. So we draw an arrow, which implies the 2 electrons in the lone pair attack the carbonyl. We draw a double-headed arrow, the electrons go up to the oxygen, then back down, kicking out the chloride, to give us an acyl pyridinium salt with a chloride counterion. So when we looked at the aromatic system in the pyridines, we saw that because there's an electronegative element in the aromatic ring, the whole system has lower energy, which means it is a better electrophile but a worse nucleophile. So if we're looking at pyridine as electrophile, we should see more reactivity than benzene. Another way to consider this is if we think about what happens in the non-aromatic systems. If we have alkenes, well, we don't expect alkenes to react with a nucleophilic carbon species such as phenyllithium, whereas we know that the corresponding nitrogen analog, so an imine, reacts very quickly. So when we apply that to our aromatic system, what we have is a nucleophilic attack of carbon reagents at the 2 position of our 6-membered heterocycle. We have a nucleophilic attack at the 2 position because the resulting anion is stabilized on that electronegative nitrogen atom. In this case of pyridine, we don't isolate this immediate product, but because the aromatic ring, the aromaticity is restored by reaction with trace amounts of oxygen in the atmosphere of the reaction. So, our pyridine is an aromatic ring, but the aromatic ring is a good electrophile because it contains electronegative nitrogen. That means the system is polarized in very much that the imine is polarized versus the corresponding alkene. That means that when we have a good nucleophile, a carbon nucleophile, such as methyl lithium, then the methyl minus can attack our system, and it attacks at the 2 position, same way it would attack an imine. That gives us a new carbon-carbon bond and a stabilized negative charge on the electronegative nitrogen atom. So in this system, subsequent reactions with the oxygen restores that aromatic ring. We get a similar reaction with amide nucleophiles. So if we treat pyridine with sodium or lithium amide, we get what's called the Chichibabin reaction. So what happens is, in a similar reactivity, we have attack of the nitrogen, the nucleophilic nitrogen, at the 2 position. That gives us a negative charge stabilized on the electronegative nitrogen atom. But this time, we restore aromaticity by the loss of H-. So if we draw this arrow, we can see the negative charge coming in and H- coming back and deprotonating our ammonia solvent. This is a very unusual reaction mechanism because it is very unusual to see the loss of H-. But in that case, that restores our aromaticity and turns our pyridine into a 2-amino pyridine. So, looking at that in more detail, when we take pyridine, and we treat it with the lithium salt of ammonia, so Li+, NH2-, in ammonia solvent, then as before, we get a nucleophilic attack of the NH- onto the pyridine. The attack proceeds at the 2 position and it breaks the aromatic system. The result of this first step is that we have a new nitrogen-carbon bond, and the negative charge is on the nitrogen. That is good because the nitrogen is electronegative. So we can say the negative charge is stabilized on the electronegative nitrogen atom. In order to regain aromaticity, we need something to leave, and in this case, our negative charge is going to come back in and is going to kick out H-. That H- will deprotonate one of the ammonia molecules and give off hydrogen gas. The resulting product from this reaction is then the 2-amino pyridine compound. As well as more of our lithium amide starter material and, unusually, hydrogen gas. So we saw at the start of this lecture that pyridine will react with an electrophile. So our nucleophilic nitrogen lone pair will react with our acid chloride to make a pyridinium salt. Well, this salt has a permanent positive charge on the nitrogen on that aromatic ring, and as a result, the whole system becomes much more electrophilic. So we can see, exactly as before, we get attack of a nucleophile, this time a Grignard reagent, at a 2 position. However, we also get some attack at the 4 position. And in fact, by changing the size of the R group, we can change the ratio. So if R group is a methyl group, will get 70% attack at the 2 position, 30% attack at the 4 position. But if the R group is a bulky tert-butyl group, that shifts to a 50-50 ratio between the two. So, first of all, to make the pyridinium, that lone pair in our aromatic ring is not part of the system, so it's a nucleophilic lone pair. That means if we put in an electrophilic acid chloride, the lone pair will attack the carbonyl and then the double bond will be formed, kicking out chloride leaving group to give us a acyl pyridinium species with a chloride counterion. At this stage, our Grignard reagent, nucleophile, can attack at the 2 position to make a new carbon-carbon bond and to neutralize that positive charge on the nitrogen atom. However, because we have that group on the nitrogen atom, and that group is reasonably large, we get steric clash between the group and that 2 position. So we also see attack of our Grignard reagent at the 4 position. So the electrons still move around the ring to quench that positive charge on the pyridinium species, but this time we end up with our 4 substituted product. And by increasing the size of that ester group, we can change that ratio further. So what happens if instead of our bare pyridine ring, we have a leaving group on there? So something like a chloride, bromide, fluoride, iodide, or mesylate. Well, then we can get substitution. So for something nucleophilic, for example, OMe-, can attack at the 2 position very much like the carbon and ammonia nucleophiles. But now we have that leaving group, so that negative charge that was stabilized on the electronegative atom can come back in and kick out the good leaving group. This works really well when our chloride is in the 2 position of the pyridine, and it also works really well when the chloride is in the 4 position. Again, the methoxide comes in, we can push the arrows around the ring and stabilize that negative charge on the electronegative nitrogen atom, pushing the electrons back through to lose our very good leaving group, chloride, and regain aromaticity. However, in the 3 position, we can't do this. There is no way, because of the symmetry of our 6-membered ring, that we can put that negative charge resulting from the initial attack of our methoxide on that electronegative atom. So that doesn't mean that this reaction doesn't work, because the entire aromatic system is still electron poor. That electronegative nitrogen element does lower the energy of the ring, so we can get displacement of that chloride, but it is significantly slower than the other 2. So, going through the mechanisms a little bit more slowly. If we have a pyridine that has a leaving group at the 2 position, and we react that with a nucleophile, such as methoxide, well then we'll get attack of that negative charge on the oxygen to our electron deficient ring. We'll make a new bond between that oxygen and the carbon, and the resulting intermediate will lose its aromaticity, but it will have that negative charge stabilized on our electronegative nitrogen atom. Aromaticity in the system by taking that negative charge, pushing it back in and losing the good leaving group of chloride. And that means we're able to swap our nucleophile, in this case OMe-, with our leaving group Cl. So if we look at the rates of reactivity, we can see that taking the 2-chloropyridine as a benchmark, our 4-chloropyridine is slightly faster, but both of them are significantly faster than the 3-chloropyridine. If we take the chloropyridine and we react it with an electrophile, so the nucleophilic lone pair reacts to form the methylpyridinium salt, well, now we have an even more electrophilic system. There is a permanent positive charge on that ring, so that the rate of reaction is increased even more. To start with, we'll again go through the mechanism whereby our lone pair, which is not part of the aromatic system, of our 2-chloropyridine can react with a very good electrophile, something like methyl iodide. We make a new nitrogen-carbon bond, and then we break a weak carbon-iodine bond, giving a good iodine- leaving group. And this gives us the corresponding pyridinium iodide salt. Because there's a permanent positive charge on that nitrogen atom, the entire system is much more electrophilic, such that when we have our nucleophile, in this case methoxide from sodium methoxide, we're going to get a rapid attack at 2 position that's accelerated because we make a new carbon-oxygen bond. We break the aromatic rings, but we have neutralized that positive charge. However, we can regain aromaticity if we use the lone pair to push back in and promote the loss of Cl-, which is an excellent leaving group. Therefore, overall, we get substitution of our chloride for our nucleophile. And again, this is faster than the uncharged version because the charged version is a better electrophile. We can go back and look at the complete series now, where our 2 charged species are significantly faster than our 2 neutral species when we have our leaving group in either the 2 or the 4 position. These are the fastest because in those 2 positions we can get stabilization of the intermediate by either quenching the positive charge or stabilizing the negative charge on an electronegative nitrogen atom. There's a crossover in reactivities, and that's because our positive charged system has a charge control interaction. That means direct attack as close to the positive charge is fastest, therefore a 2 attack is faster than a 4 attack because the attack is further away from the positive charge. Whereas in the uncharged system, it's an orbital control system. That means that it's soft and orbital based, and the biggest orbital coefficient is on the 4, the position where the chloride is, versus the 2 position. Now, these are both faster than the corresponding 3 substituted, but we do still see substitution at these positions. In fact, the positive charge on our pyridinium species means that now the rate of substitution is pretty decent. However, our uncharged species is still pretty slow, but not nothing, like for example in chlorobenzene. However, we get some strange reactivity when we look at this kind of system. So again, this is a 4-chloropyridine, and we have an NH2-. What we might expect is a substitution reaction where we end up with a nitrogen where the chloride once was. And in fact, if we look at the products from this reaction, we see that's exactly what we get. However, as well as getting a substitution where we expect in the 4 position, we also see some substitution in the 3 position where we don't expect it. What's strange is that if we start with a 3-chloropyridine, we get the same ratio of the same products. Now, if we start off with 2 different starting materials under the same conditions and we get the same ratio of products, this strongly suggests that they're both going through the same kind of intermediate. So what's actually happening here is instead of nucleophilic attack, our sodium amide is behaving as a base. So it's promoting the loss of HCl from the start material to form a triple bond. Now if we look at that triple bond, it's a triple bond in a 6-membered ring. It's what's known as a pyridine, and is extremely reactive. As you can imagine, the strain from a triple bond, which wants to be 180 degrees, is significant, and therefore there's rapid reaction with a second molecule of our NaNH2, but of course the reaction can be at either end of our triple bond, which leads to this mixture of products. So if we take either of our 2 or 3 chloropyridines and react them with a sodium amide base, what we will have is deprotonation and loss of Cl. So overall loss of HCl from our molecule. That means that both of these 2 starting materials go on to form the same 6-membered ring with a triple bond, so a pyridine species. This triple bond, which wants to have bond angles of 180 degrees, is extremely strained. And therefore it reacts rapidly with an incoming nucleophile. In this case, we have our NaNH2, which was the base in the first step of the reaction, can now be our nucleophile in the second step of the reaction. But of course it can attack at either end, and that leads to a mixture of products where we have a new nitrogen atom at the 4 position or a new nitrogen atom at the 3 position. So we've looked now at how our 6-membered nitrogen-containing aromatic heterocycle or pyridine behaves, or what happens when we look at more complicated versions of the same molecule. So in fused heterocycles such as isoquinolines and quinolines, or in heterocycles with extra heteroatoms in, such as pyrimidines. Well, in the isoquinolines and quinolines, they're still electron poor because they have this electronegative element, but we'll have more electron poor properties on the nitrogen containing heterocyclic part and less on the carbon containing part. In our pyrimidine, we expect these things that we've seen so far to be enhanced, because now we have two electronegative nitrogens in our aromatic ring. So, in the same way we saw reactivities between carbon nucleophiles and pyridine, we get attack of carbon nucleophiles and isoquinolines. We get attack directly next to the nitrogen as if it was an imine, and that goes on to make a new carbon-carbon bond. This is a stabilized intermediate because that negative charge is stabilized on the electronegative atom. In this case, we don't see oxidation with air because the whole aromatic ring hasn't been interrupted. Only half of it has been interrupted, so there's not such a driving force to regain aromaticity. The same thing we see with carbon nucleophiles, we can see with nitrogen nucleophiles, so in the Chichibabin amination reaction, again, we'll have attack at the two positions next to that nitrogen, which gives us a new nitrogen carbon bond following oxidation with some kind of external oxidant. Nucleophilic substitution works really well as well because we have this electron poor system. Again, what we want is a nucleophilic substitution whereby our nucleophile can attack, give stabilization of a negative charge on our electronegative nitrogen atom, followed by the electrons funneling back through and keeping out a leaving group. In a system with more heteroatoms, well then, this rate is increased further. So for example, if we have this dichloropyrimidine, we have a good nucleophile, so methylamine. The nitrogen will attack, we'll get stabilization of that negative charge on the electronegative nitrogen atom, followed by restoration of the aromatic ring and loss of a chlorine. What's interesting here is because we have swapped an electronegative chlorine for an electron donating nitrogen atom, the reaction stops after one iteration, because the product with one nitrogen and one chlorine substituent is not as electron poor as the starting material with two chlorine substituents. This is an interesting reaction because we can see this is very similar to some of the structures seen in DNA bases. We started this video looking at that nitrogen lone pair. It is the highest occupied molecular orbital, and this is very important in the reactivity. So it can react with acids and it can react with electrophiles to form pyridinium salts. In general, we saw that because the aromatic ring is made up of an electronegative atom, 6-membered aromatic heterocycles are electron poor, and therefore good electrophiles and react well with nucleophiles. Carbon nucleophiles will react at the 2 position of pyridine, as will metal amide nucleophiles, and in each case we get oxidation. In the case of carbon nucleophiles, we get spontaneous reaction with the air, whereas with nitrogen in the Chichibabin reaction, we get loss of H-. We can see that if there's a good leaving group in the system, we can get substitution. However, under certain conditions, we can promote an elimination instead of substitution to have a reaction that proceeds via a strained alkyne. This reactivity does not just apply for pyridines, but can be mapped across other 6-membered heterocycles, such as fused heterocycles like quinolines and isoquinolines, and heterocycles containing multiple nitrogen atoms. Thank you for watching. See you next time.